Okay, so we've talked about the more complex part of this lesson. Now, in this second half, I'll basically talk about uh, the line following implementation. So this is something much simpler than what you saw in all of these examples, but it will use the on and off controller that I talked about right here. In fact, you can get a very good line following implementation by just using this technique right here. So before we get into that, I just want to talk about the sensors involved in this. So as far as your proximity sensors are concerned, you only have to rely on an IR sensor, your infrared sensor. So if you recall from last week's session, your infrared sensor basically sends out an infrared light, and that can basically that is so. In the case of a line following robot, you need to first define a path, like a ground path. So based on the reflected value of your infrared sensor, it can basically tell you whether your robot is in the line or outside the line. So, and your localization sensor. Okay, so Alan asks, what is the range of the IR sensor? That's a good question. And I don't have the right answer immediately because it sort of depends on the manufacturer. So cheaper manufacturers, I like the ones that you see here, right? I don't think these are very sophisticated. I don't think they'll be able to send stuff, say, more than a couple meters. So I've actually not used the IR sensor in real life, but I've used like ultrasonic sensors from similar manufacturers, and they will fail after a distance of say 4 meters. So I assume that the quality wise of this is also, comparable. Yeah, they also have a minimum range. So as far as ultrasonic sensors are concerned, they will not work if you place an object within 3 centimeters of the sensor. So that is something that you need to keep in mind for real robots. That is a very good point. And usually when you buy sensors, right, you can have that information given to you in a specification sheet. But for as far as the VREP visualization is concerned, you don't have to worry too much about that. Yeah. So this is a proximity sensor that you need to be using. And it's also good to have like a localization sensor. Whenever you're working with mobile robots, your localization sensor will basically tell you how far you've traveled. So it's always nice to have that. And as always, the more sensors that you use, the better your results will be. So I know I've talked a little bit about adding more sensors and all that, both in this lesson and in the previous lesson. But there is like a valuable lesson to that. So if you follow the story behind Boeing, the Boeing 737 Max, the plane that crashed a couple of years back, I think last year, yeah. If you watch the story behind that, right, it basically boiled down to them relying on a single sensor. So you can see that it had catastrophic effects. Of course, there were many other problems associated with the whole airplane, but it boiled down to them having a control system just rely on one single sensor reading. So you can basically see how disastrous you can be. So yeah, that's just a business case study for you guys to know. Okay, Alan also asks, so if I use this, will it be able to detect the objects in my path? Yes, it can. But they'll have to be, basically, the line of sight will have to be different. So for example, if this is to detect whether or not a robot is following a path, its line of sight needs to be below the robot. Basically, it needs to be facing down. If you need it to detect like objects within blocks of, I don't know, if you want this to detect people or something, its line of sight needs to be perpendicular to the ground. So yes, it can be used for both applications. That's the whole purpose of a proximity sensor. It's basically to detect objects. Okay. So this is a simple pictorial representation of how your algorithm should look like. No, I know I talked about having multiple sensors, but here the green sensor is a single IR sensor. Your orange box is your robot, and here is the line that you want to follow. More specifically, this is the edge that you wish to follow. So your on and off controller, right? It has two states, on or off. So as far as a mobile differential drive robot is concerned, what do you think the two states will be? So it's essentially turn left or turn right. So I'll show you the demonstration in VREP. So what this essentially will do is your robot will sort of always be turning left or right when it reaches a corner, because that's how the algorithm is designed. But it still manages to do a job. So suppose it's moving it's moving along the edge. You won't have to do anything. But if you stray from the edge to the right, you'll have to make a corrective action and turn to the left right here. And you can do that by increasing your right wheel velocity with related to your left wheel velocity. And the same case applies if you stray to the left. If you stray to the left, you basically have to do a right turn, and that is to increase your left wheel velocity with respect to your right wheel. So that's essentially how the algorithm looks like. It's not too complicated, but it does the job. Does the width of the black line matter? Yeah, actually, it does, yes. If your light bulb is basically too wide for it, it might not even pick up that, okay, it's a black line. So for example, this line right here is black, and the ground on which the robot is operating is a white surface. So there needs to be a sharp contrast between the line and the operating environment. Only then can the sensor pick up that there is a difference. And if the line is, say, too thin, it might not be able to pick up that difference. So yeah, that's a good point. So that is basically what I want you guys to do in your final, in this lesson at least. So I'll basically show you a simple version, simple implementation, but it's up to you guys to make the implementation more complex. Like for example, I've just shown a simple line here. You can probably make different tracks, like a circle, like keep rectangles, but don't keep the rectangle corners too sharp. Otherwise, your robot itself might have difficulty turning. But yeah, it's all about sensors to add more redundancy. But yeah, it's all up to you. And if you manage to finish this using your on and off controller, you can even try implementing a PID version of this. And your pseudo code will look something like this. So you have your three components right here. Yeah, your KPs, your proportional, then you have your integral and derivative. Your error point is basically the different distance between the center of your line and your robot. You'll sort of understand this in greater detail once you start implementing your on and off controller and see its disadvantages. So that's how I would want you to do as far as the timeline is concerned. I would first want you to implement your on and off controller, and then if you want to make things more elegant or more complicated, then you can try your PID controller. And here are some links to all of the things that I've discussed above. So here RL is basically the algorithms that enable all of this. Yeah. So it's also the same algorithm used in self-driving cars. Just another tidbit. And the control strategy used in, your NASA's Apollo mission, the moon landing mission, that used something called an optimal control. I've left links to all of that in case you're interested. Now, since you also showed that you were interested in making your own PID controller, I can, in the next lesson, I'll throw in some mathematics for you guys as well.